Hi guys, how is everyone doing? Oh, hi Jonathan, how's going? How are you doing, guys? Welcome to the episode number 5 of Quantum Programming Livestream. I'm your host, as usual, Marek Narozniak, and today we are going to talk about the Schrödinger Equation. I learned how to pronounce it before the stream, and yeah, let's get it started. But before we actually start, there are two very important things I have to do, which is little advertisement first. Just pull this up. So guys, I accidentally opened the browser. Hi Tim, how's it going? So these two videos are videos we recorded with Tim, where I speak a little bit about quantum attacks on Bitcoin. We think those videos didn't get enough attention, not as much as they deserve. So guys, feel free to check them up. I will leave some links in the description. And now I will prepare myself something nice to drink and we can get this Schrödinger thing going. Oh, on Twitch, great. Yeah, I haven't seen you stream on Twitch yet, only participate. Hopefully no technical problems today. And hopefully there will be Bill Murray watching us, as usual. We all praise Bill Murray. What I prepared for today, before the foam of my beer falls down, is yeah, we all like Bitcoin, right, Tim? So today we talk about the Schrödinger equation. There will be two little challenges. First, we will, I don't know if you guys remember. Yeah, na zdrowie. Cheers. I don't know if you guys recall, in the episode 3, we did some coin flip simulation. Today we will do something similar, but we will use Schrödinger time evolution, not unitary evolution. So before we get started, let me pull up the Schrödinger equation just so that we can take a look at it. Where are you, Schrödinger? Here. And also maybe a little meme. Do you guys like memes? You guys can take a look at the meme while I talk about the equation. So yeah, this is a differential equation, and at first it might look a bit scary, but you don't really have to worry about it, because if you like to do numerics, if you want to do numerics, actually all you care is what you can get out of it. And in this case, there are basically three relevant things on this equation. This is the time-dependent form. This is the one that we're going to be using today. And this is the one that is used in QDIP. So you have, on the right-hand side, you have two things. Hi Manish, how's it going? You have two things. You have the quantum state, psi of t, and the Hamiltonian operator. And on the left-hand side, you have a time change, basically. So what this equation tells you is how your quantum state will change if you apply Hamiltonian H on it. So there are three things there, and whenever you have two of those things, you can get numerically the third one. So if you have Hamiltonian and the state, by solving this equation, you can get how the state will change. If you know how the state changed and you know the Hamiltonian, you can get the previous state. Or if you know the previous state and you know how it changed, you can get the Hamiltonian. That's basically basically how it works. There's really nothing special there. So how about we talk a little bit about the challenges. So the first challenge is we are going to, let me just read it for you guys. Perform a time evolution that would flip the 0 into 1. Plot the fidelities of eigenstates of the operator and magnitudes of the Hamiltonian operator terms. Do it once using square shape potential and once using the Gaussian pulses. So that's the first challenge. Let's get it started. So where's our episode 5.py file? So let me just look at my cheat sheet, because without it I'm basically helpless as usual. So, well, there are a few things we always use. It started with NumPy, and of course we will need quantum states, so we import basis. The challenge asks to flip, so we will need sigma x operator. And yeah, I guess, oh, and Schrödinger equation solver. Actually, MeSolve is a master equation solver, but it automatically detects the case of the Schrödinger equation, so that's basically what I like to use the most. I also prepared a little plotting function just to save us some time. Plot time evolution, which will plot both the potentials and fidelities. So okay, challenge 1A, say. What are you guys drinking there? Something good? So, first of all, we will produce a vector that will create a discrete, discrete representation of the time space. So this is basically all the time steps. Actually, let's do it for pi. And time units are in pi. 50 steps is enough. And we return the delta t. Sorry, dt. Actually, let's parameterize it. Let's set the resolution to 50, like this. By the way, guys, feel free to let me know if everything works fine, if you can see me clearly. If not, I don't think there's anything I can do with that, but still good to know. So, well, the challenge says that the initial state is 0, right? So let's make it. That's the state. And we flip it, so the Hamiltonian operator is... Actually, let's not look at this meme, let's look at the equation instead. Yeah, the Hamiltonian... So, yeah, so psi 0 is the h of t on the right-hand side. Hamiltonian is sigma x. What else? And to compute it, using QDIP, we basically use the master equation solver, which handles the Schrödinger equation as well, times. You're having coffee, Manish? Oh, tea time. Jonathan, are you saying that you're not having beer at 10 a.m.? Why not? So, well, that's all we need to just sort of compute it. But we need to perform some sort of measurements to know what is going on there. For this, we can pass a measurement function. Let's call it, I don't know, we need fidelities, right? So let's call it getFid. This function will accept a, well, time step and the quantum state at this time step. We need to compute the fidelities. The challenge says of eigenstates of the operator. So we get the fidelity of the zero state. Wait. Guys, you know what's the true challenge of this live stream? The true challenge is to finish the challenge before you get totally wasted. That's the true challenge. It's not the challenge. Moved back to YouTube. Welcome back to YouTube, Tim. Actually, right after this, we are recording a video with Tim, which will be released this weekend. And we just return a list of them. So let's make it, which order would be good? Maybe 0, 1. What? Yeah, I can have a beer at 10 AM, of course, but the rest of the day will be not as good as I planned. Man, the secret of happiness is not planning. Did you know that? If you don't plan things, that's when you're happy. Alright, let's run it. It won't really show us anything, but just to know it's fine. Hold on, solutions. Python episode 005.py. Yes, a response to Veritasium video. I totally fell for that one. By the way, Tim, I watched Seinfeld yesterday, and I'm totally influenced by your your opinion of Jerry Seinfeld. I no longer really like this character. Oh, import error. Oh, there's a typo here. But yeah, I do like George. I admit, I do like George. Very underappreciated character. So about this Veritasium video, it's about energy transfer, not going through the wire. I totally fell for that. Me solve. Got an unexpected keyword. EOPS. Alrighty. Should be OPS, because it's operators and not epurators. Alright. It's good to do those sanity checks once in a while. Seinfeld, yeah. Tim, did you know that in Europe people don't really know Seinfeld? Like, Jonathan, have you ever seen Seinfeld? Like, I don't think so. Everyone saw Friends, but Seinfeld, no. Alright, it runs. Good. So let's make some plots and measurements. So we can get the measurement array, which is going to be a list of lists. So let's convert it to NumPy array so that we can transpose it. Expectation value. So this will contain all the measurements from the getFit function, and we can extract the fidelities by basically transposing it. So the first one is going to be fit0, because first one is fit0 here. The second one is going to be fit1. That looks good. And to plot it, I need to construct like little data structure I designed, like this. So here we have fit0, not 9, 0. It's because of my contact lenses, guys. Let's do a little LaTeX here. So this is psi at the moment t. Psi, sorry, just 0. Absolute value squared, right? That's the fidelity. Last time I checked, that was the fidelity. I think the Pope has not updated the definition yet. So that should be fine. I think we're fine here. Seinfeld was huge, even in Australia. Yeah, but in Europe, somehow nobody knows it. Like, now is the first time you can actually watch Seinfeld in Europe. It's not like it was bad or anything. It's just nobody was really familiar with that, you know. I don't know why. People in New York City were also very surprised when I told them. And let's also make potentials. Potentials, so here is just constant sigma x. So we are just going to make a bunch of ones, because it's just constantly 1 for pi time, or pi over 2, pi. Wait, so this is resolution, right? I think that's the resolution. And the label for that is okay, the beer definitely starts to work. Sigma x. That will show them. And now let's plot it. Plot time evolution times fidelities, potentials, empty string. Let's not give any title. Marks. Let's mark the moment of pi over 2 maybe. Or no, let's not mark anything actually. Let's see the plot first. File name equals rest of PNG. Alright guys, everyone please do a little prayer because I'm about to run it. What? Evolution. Evolution. Time evolution. I can't even type a phrase correctly when I'm sober, and now it's even harder. This is marks with S because it's a list. Yesterday with Tim we got those big Asahi beers, like 1 liter glasses. It was crazy. I slept so well after that. Alright, let's check the result. It finished running. The result is in the file rest.png. Is that how I called it? Yes, it's the one. Okay, that looks sort of nice. So the blue curve is the probability of measuring 0, and the orangish curve is the probability of measuring 1, and I can see like it flips it and flips again. So we time evolve it for too long. That should be pi over 2. Just run again. Oh yeah. And the food was so good. It was totally worth waiting. Bang! We got it. Okay, so we made a physical Hamiltonian, which is very simple, sigma x, constant 1, that runs for pi over 2 time. And makes us the, well, it starts, you can see that at the beginning, blue line is at 1, orange line is at 0, and they just swap. So it basically flips 0 into 1. So, okay, what's the next thing? Let me just check the, I forgot. Okay, same thing with Gaussian pulses. So now we are going to do the same thing using the Gaussian pulses. There's my shell. Okay, our timing is not perfect, it's already pretty long. Okay, so let's just wait. Let's just rush it. Challenge 1b, which is going to be same thing but with the Gaussian pulses. So we take the liberty of just copying all this, and we will change the Hamiltonian. So Gaussian pulse, This is going to still be sigma x. However, now the potential is time dependent, so it's not just constant 1 anymore. It is going to be described by a function called f. Let's define this function. This is going to be the Gaussian function. Naked online strips without something. Thanks for the comment. That's wonderful. I hope I will never need to use that, but you never know in life. Okay, so that's going to be a lambda expression, which takes a time step and some arguments, which we will just ignore. And we can make our Gaussian pulse here. So Gaussian pulse is defined like minus a t minus b, where b is the center, squared. That's the thing. Oh god, this spam bot just keeps... I mean, what can I do? What can I do? I guess I'm popular. So here, well, I will give you the magic values I computed today at the grocery store. B is pi over 2. Time evolution is going to be for pi. And yeah. Oh, and we also need to scale it. Don't worry how to choose those values, because in reality, you can always just plot things and check if integral equals pi over 2 of the entire thing. So there's many ways you can achieve literally the same thing. And will that do? I think that will do. Let's add a mark at pi over 2. Let's run it. Don't click in that link, everyone. Don't click it. I don't recommend clicking it. Okay, well, it does what we need, but we forgot to plot the right thing in the potential. So let's just replace those ones with f of times, and let's not give any arguments because it's not relevant. Let's just run again. Yeah, don't click it. naked-hd.xyz, my true fan. Alright, that's a nice, beautiful Gaussian pulse. Gaussian pulse is basically pew pew kind of thing, you know. So before it was, okay, it looked just like straight line, but imagine it's just like sudden jump from 0 to 1, proceeds until time equals pi, and then suddenly jump from 1 to 0. And that's like pretty difficult to achieve. It's easier to just make pew pews, like, you know, like that. So that's what we did now. See this nice pew pew curve here in the potentials? It achieves the same thing. It starts in the blue, ends up in the orange. So, okay, challenge 1 done. Let's see what was the challenge 2 about. Okay, repeat the coins challenge 4 using time evolution. Hold on, challenge 4 was Jega. Let's just copy that so that we see it in front of our eyes. Is this a gaming live stream? You wish. I wish. It's more fun than gaming. Quantum is more fun than games. Don't you know that, Tim? Okay, what was I? Shell. So let's just, okay. 2 coins are placed heads on the table. We throw the first coin, and if it lands tails, we also throw the second coin. Program a quantum simulation of that scenario. Provide quantum circuit and histogram of counts of measurements outcomes. So we already did that. You can check episode 3 if you want to know how it works. But what I will do now is I will just quickly show you the plot we need for this. Wait, I'm already drunk. Solutions, no. Oh yeah, it's a challenge for it, yeah. So basically the outcome should be like this. So we would need like 50% chance of getting 0, 0. So half of the times we would measure 0, 0. We would never measure 0, 1 because the second coin is never thrown, you know, if the first one is 0. So that's like impossible. And the rest is evenly distributed. Yeah, I need to learn some Chinese, seriously. Need to pick it up. Alright, let's do some copy paste. Wait, that was supposed to be resolution here. Parameterize stuffs, guys. So there will be 2 Gaussian pulses. If you remember the episode 3, there was 2 gates applied, so there will be 2 pulses. Okay, so that is going to be a 2-qubit system that starts, if it's a 2-qubit system, we need tensor. And I will import some more gates, sigma y and sigma z. I will not explain you how the Hamiltonian works. That's pretty much out of the scope of this video. But if we do some whiteboard videos someday, then I will be happy to. I derived it today at the grocery store again and showed it to Tim like 1 hour ago. He said the coefficients look weird, but I fixed it and it works. So it starts in 0, 0. We flip the first one. So that's going. So there will be like 2 Hamiltonians, right? First one is going to throw the first coin. So that's like a Hadamard gate, which can be achieved by just doing sigma y half step. So yeah, let's call it HSX, whatever. Although it should be HSY. And tensor. We throw the first coin, so it's in the first one. And second one is not affected, so it's just identity. Which reminds me I should import the identity operator. Okay. Okay, everything is aces so far. And the second pulse is going to be this magical thing I derived. 1/2 times tensor 1 plus sigma z and nothing, just identity. This is like outcome per outcome kind of derivation. And another, so that's the subspace of where the coin landed tails. So that's is going to be 1 minus sigma z. And here we do actually apply sigma y, just to rotate to the plus state. Sorry, to like, yeah, plus state, like halfway between 0 and 1, which is like the coin flip, coin toss. Okay, the magical values, this stays the same. And now we sort of need 2 magical functions. So this is going to be f1. the magical values I have found earlier, minus pi over 2, because there are 2 pulses now. And actually the whole evolution has to be longer now, because it needs enough time to apply 2 gates. So it's 2 pi. And the next pulse is going to be exactly the same, just delayed in time. Let's call it f2. So this is going to be like 3 pi over, 3 pi over 2. They are separated by 1 pi. Cieszy Jega, yeah. Don't make me laugh. Our Chinese. We don't need this B stuff here. Okay, so Hamiltonian. Hamiltonian is definitely going to be different. So we do HSY according to the first pulse, and then HCC according to the second pulse. So far, so good. Now we need to sort of update our measurement. So there will be more outcomes to consider, like 4 of them. Yeah, for 2 qubits, it's 4 outcomes. Tensor, basis, not Bezos, basis. I don't know what is this beer, but I can barely see. Is this methanol stuff or? Okay, 4 outcomes. 0, 0, 0, 1, 1, 0, 1, 1. Let's not forget to update here, because that would be pretty much a failure if we forget that. 1, 1. And of course, we have to return all of them. Nah! Okay, that's good. So that's our measurement. A bit more complex, but oh, we also need to extract those values. 0, 1. 1, 0, and 1, 1. And these, okay. Bear with me, guys, almost there. I need a drink. Delicious. Okay, 4 of these. 4 of these. Let's do it like line by line for aesthetics. Aesthetics really are important in life, guys. Respect aesthetics. I told you to respect aesthetics. Why it? Okay. Bear with me, almost there. Okay, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. And here now we have 2 functions, f1. So that's, how did I call it? Let's call it hy. And the other one is going to be hc, because I just want to have 1 character in the subscript. Okay. I think this is nicer. Let's make 1 more mark. Pi over 2. Alright, guys. Little prayer time. The spice of Tim. The spice must flow. He who controls the spice controls the universe. Okay, line 63. Okay, this is the fidelity measurement. Parenthesis problem, as usual. Come on, we can do it. All up. Ah, okay, there's one parenthesis too few, because we added the tensor. Manish, there are spices, and there is the spice. It's not the same. Okay, I think we got it. Okay, it runs fine, except for the warnings, but we don't care about the warnings. Let's check it. Actually, I already have this buffer open. Yep, beautiful. We got it, guys. So you see two pulses. The blue pulse is the first gate. The orange pulse is the second gate. And you can see the system starts in the blue curve, which is 0, 0 state. After the first coin is thrown, it becomes like even superposition between 0, 0 and 1, 0. So you have like 50% chance of measuring 0 or 1 on the first coin, but the second coin is always 0. And then after applying the second gate, which is our controlled Hadamard, you also get even superposition between 0 and 1 on the second coin, but only in the subspace of first coin being 1. So that you can see on the red and green curve. And the orange curve, which is 0, 1, which is the impossible state, it's always 0. So thing works. Hell yeah, Tim. Cheers to that, guys. We solved it. That was totally unexpected. So we are approaching 40 minutes of the live stream. I'm already pretty red and drunk, and we solved all the challenges. So I guess we should conclude, and I'm going to do a video with Tim now. So thank you guys so much for watching. It was great to have you here. Thank you for writing messages. That was episode 5 of Quantum Programming Livestream. My name is Marek Narozniak, and see you next time. Oh, no, not see you next time, not see you next time. One more thing, guys. One more thing, don't leave yet. Next episode is going to be episode 6, Quantum Adiabatic Computation, requested by Emil. And now we are good. Now we are ready to conclude. So, once again, thank you again for participation, and cheers, guys. Bye.